Good evening, everyone. Thanks for joining us for our Caltech Astronomy Stargazing lecture. We've got a great evening planned for all of you with a live demo in the middle of the presentation as well, so it's going to be very exciting. I'm Dr. Cameron Hummels. I'm a research scientist here who organizes these events, and let me just lay out our schedule for tonight. So I've got a few announcements that'll take a couple of minutes, and then we'll get started with the overall program. I'll introduce our speaker, who's going to talk for roughly 30 minutes about the history of transient astronomy and these cosmic fireworks that are going off that we're only now really recently been sensitive enough to be able to detect, and what we're learning from those objects and those observations. And following that presentation, we'll have like maybe a few questions of Q&A just following that with all of you. And then it'll kind of switch to a choose your own adventure style part of the evening. We will have telescopes that are being set up as we speak right now in the athletic fields behind this auditorium. And we'll move the table in and set up a Q&A panel consisting of our speaker, myself, and two other members of the department who will be here to answer whatever questions you may have about astronomy or physics or space science. And that could be related to the content of the presentation about the transient astronomy, or it could be about, something that you read in the New York Times or whatever about space and astronomy, and you really want to figure out what the answer is. So you can ask us. We work in a variety of different fields, and hopefully we can respond and provide an answer to your liking. These events. Oh, and on the field, the weather's quite clear, so we have pretty good stargazing tonight. I think we're going to look at potentially the Ring Nebula. This is this planetary nebula in the sky that's really cool to look at. We might look at a globular cluster of stars, the Hercules cluster, and maybe some other objects. So it should be good. And both the Q&A panel in here as well as the stargazing session will go until about 9:45. So you've got plenty of time if you want to go look at the telescopes and then come back in and ask a question, or vice versa. You can go back and forth between the two stages if you want, or you could just be like, I'm heading out, I'm tired, and so you can leave if you want to. So these events take place once a month on Friday nights. We actually had another one this month. We had one last week that was entirely in Spanish language about black holes and gravitational waves. It's on our YouTube channel if you're interested in checking out, but I highly recommend checking it out only if you can speak Spanish, because it might not make a lot of sense. I mean, it still might not make a lot of sense if you do speak Spanish, but it was a good presentation that Javier gave. Our next one of these will be October 3rd, Friday, October 3rd, a little over a month from now. And the topic will be all about near Earth objects. So these are asteroids that have come into the inner solar system and might pose a threat to impacting the Earth, might not pose a threat. And these objects formed in the very early solar system. So as we study them, we can learn about the state of our solar system 5 billion years ago, which is quite revealing. So that'll be here in a month. Other events. We also do an event series called Astronomy on Tap that takes place a couple of miles from here at the Doghouse Beer Garden in Old Town, Pasadena. Those events feature two 15-minute to 20-minute presentations by different astronomers or space scientists, as well as astronomy-themed pub trivia, live music, and such. And like these events, they're totally free, and they're at a public level. They're open to the public, and we get a few hundred people who show up to those. Our next one of those will be on Monday, September 15th, and the two topics will be, one will be about the possibility of settling on Mars, like living on Mars in the near future or distant future. We're going to talk about that. And the other will be about sending up telescopes on big high altitude balloons to get above much of the atmosphere, so that you can, it's almost like a space telescope without the rockets. You bring it up on a balloon and you can take observations. So this engineer and scientist works on balloon-borne telescopes. They're both NASA Jet Propulsion Laboratory engineers who are going to be discussing this. Adam Stelzner and Susan Redmond. Let's see. Other announcements. We here in the department help with dark sky festivals at a number of different national parks throughout the year. And there are two coming up next month, one on Friday through Sunday, September 12th, in Sequoia National Park, just a few hours to the north of us, the big trees and the mountains in the Sierra. So it's like a 4 or 5 hour drive, depending on how quickly you drive. And we'll be there along with many other volunteers hosting public presentations, much like the one that you're going to hear tonight. In fact, Sam is going to give this talk in a few weeks. So if you're like, I really like that talk, I want to hear it again, you can come hear it again. But there will be a number of other talks, both from scientists here at Caltech, as well as other scientists talking about astronomy, and as well as telescopes, a big star party with like 30 telescopes set up in the forest with views of the sky. And it's much darker, as you can imagine, outside of the light polluted areas of Los Angeles or other big cities when you get into national park areas. So that should be really fun. It's totally free. You just have to pay to get into the park. But we have information on our website and on our social media, so you should check that out. Or just look up Sequoia Dark Sky Festival. The following weekend, there is another Dark Sky Festival at another national park that we're going to be contributing to. It's called the Great Basin Astronomy Festival. I don't know if you're aware, there's another national park. It's actually the darkest sky national park in the lower 48 states of the United States. It's called Great Basin National Park, and it's in like kind of central Nevada, in the middle of nowhere, really. And that's what lends itself to having such dark skies, because it's a 4-hour drive to the nearest city like Las Vegas or Salt Lake City. So it's super, super remote, but very, very dark skies. And they too will have a series of public level science presentations and a star party with lots of telescopes. And we're going to be running a couple of Astronomy on Tap events at that. So I encourage you to check these out. Again, they're on our website and you can learn more about them there. My final announcement is that tonight, the science that you're going to hear about, or any of the nights that you come to our events and hear about the science that we do here, that science is largely funded through taxpayer dollars. Thank you very much for your support of science. And it really, it allows us to do the kind of groundbreaking technology and lead to the insights that we have about the universe. And largely the reason that we have this lecture series is to return to you, our bosses, the insights that we gain from the experiments and the research that we do. And I don't want to get partisan or political in any of this, but right now there is a major cut, the largest cut in history, to NASA, the National Science Foundation, and other federal agencies that support these grants that come to us. And it would be very catastrophic for science. Essentially, the cut is like over 50% of a cut, and it would lead to all of the science that is done here, but that you read about in the newspaper and such, just stop happening in the United States. It will move to other countries where they do support science, but so I encourage you, if you feel strongly about this, to reach out to your representatives and express your opinion that you do support science. But obviously, that's up to you. So, starting our event tonight, our speaker hails originally from Northern California, the Bay Area. She did her undergraduate studies at UC Berkeley, where she did research in physics and astronomy, primarily looking at the mass changes in black holes over the course of their lives. And here she joined our department 4 years ago and is now starting her 4th year as a PhD student in astronomy and astrophysics. And she's transitioned a bit in her research, and now she's looking more at these cosmic fireworks that she's going to talk about, these flashes or short-lived changes in the night sky that could be associated with asteroids, or could be associated with exploding stars or black holes ripping apart other stars. And that's what she's going to share with us tonight. So please welcome our speaker, Sam Rose.
Hey everyone. Yeah, like Cameron said, I got tired of working on things that take like 10 million years to change. And I started being interested in things that change over the course of a night, or the course of a couple days, or a week, or a month, or a year. And we call these objects that we see that appear and disappear in the sky astronomical transients. So let's talk about how astronomers explore the changing night sky. Well, if we're going to talk about how the sky changes, we should probably start with talking about the sky itself. So I have here a beautiful image. This was taken on Mauna Kea on the island of Hawaii. This is an all-sky camera. What astronomers actually use the all-sky camera for is when we're observing with these telescopes. So you see there at the top, there's Subaru. The closer one is Keck 1, and that's Keck 2. We actually just use this camera to look for clouds and avoid them. Which is kind of a shame because this is a beautiful image. You see the Milky Way is across the center of the image. You see the very dense regions of stars that are very bright, as well as the dark regions of dust. You see bright stars in our galaxy off the galactic plane, as well as the planet Jupiter off to the side on the left of the image. So this is sort of our fixed sky. Of course, the sky isn't totally fixed. As the Earth rotates, orbits around the sun, we're always at night seeing the space that is opposite to the sun, right? We don't see the stars behind the sun because the sun is just so much brighter than them. Over the course of a year, the sun travels through the 12 constellations of the zodiac, which have been observed in Western astronomy for a very long time. Western astronomers use the zodiac to sort of, you can figure out what time of year it is. If you look up at midnight and you see Sagittarius up in the sky, you know that it is or in the summer, versus if you look up in the sky during the wintertime, you might see Gemini. I want to talk about our early watchers. So as long as there have been humans looking up at the sky. We have archaeological evidence going back thousands and thousands of years that people have been interested in astronomy, interested in the passage of the sun, the passage of the moon, the passage of the planets through the sky, observing the fixed stars as we see them. This is for a number of reasons, both practical. If you're a farmer and you want to know when you should plant your crops, if you can tell what time of year it is based on what you see in the sky. If you are a voyager in the sea and you can measure your position on Earth based on the kinds of stars you see above you at night. If you are worshiping the planets, like the planets we know now actually all have the names of the Roman gods. If you're interested in basically, if you're living in the natural world, astronomy is a very natural way to try to figure that world out and think about it. So both for mundane curiosity, for religious reasons, and as well as just sheer practicalness, people have been looking at the sky for a really long time. I'm going to talk about one specific group of people that have been looking at the sky for a really long time and have been keeping really great records. And these are the imperial astrologers of China. So after the Warring States period in the 4th century Common Era, I'm not a historian, the Chinese dynasties became very, very interested in timekeeping. And as we already figured out, astronomy is a great way in order to do timekeeping. This is something that was actually very interesting to me as a Western astronomer that I didn't appreciate. So in Western astronomy, we very commonly use the constellations of the zodiac to divide up the sky. It turns out in Chinese astronomy, which has a more lunar focus. So they have the 28 mansions of the moon. So the sky is instead divided up into the constellations that the moon passes through over its 28-day journey around the Earth. So this is the 28 lunar mansions, which are divided into 4 larger quadrants. Some of our earliest printed maps of the stars are actually come from these imperial astrologers, imperial astronomers in the tradition. So this is a star map from the year 1092, produced by a man named Su Song, which is really, really cool to think about. So because the Chinese astronomers, the court astronomers, were doing such a good job of looking at the sky every night and tracking its changes and stuff, they saw the things that changed really easily. If you know what was there and then suddenly you see something that wasn't there before, that's really interesting. So they called these guest stars. So Kexing, I think is the correct pronunciation. And there are a whole bunch of these in the records that we still have today. They represent a variety of different kinds of transient phenomena, from comets to nova to variable stars that we see. But I want to talk about my favorite of the guest stars, which is the guest star of 1054. So if you are an imperial astronomer in China during the Song dynasty on the morning of the 4th of July, 1054, it's crazy to me that we can be that precise. The morning of the 4th of July, 1,000 years ago, and we can say with certainty, You looked out over the horizon and you suddenly saw something that wasn't there before. And this thing was crazy bright. So this was visible in the sky during the day for a period of 3 weeks. So it was stupidly bright. The records we have here, they read from the attendant sensor Zhao Bian. Your servant considers that since the 5th month of the last year, when the baleful star appeared, a full year has passed, and until now, its brilliance has not faded. So this thing was not only visible during the day for 3 weeks, it was visible for about 650 days after the initial appearance of this star. So the ancient Chinese astronomers, they didn't know what this was, but we do. So something that can be that crazy bright has to have a ton of energy. And it turns out that that energy is actually provided by the collapse of a star, about 8 times the mass of our own sun. So massive stars are in a constant battle with gravity. And this is a battle that they are destined to lose. If you think back to what you know about nuclear reactors, which maybe is not much, you might have heard there are such things as fusion reactors, which take hydrogen and fuse it into heavier elements to get energy out, and such things as fission reactors, which use something like uranium, which decays into lighter elements to get energy out. Well, if you can get energy from both fusion and fission, there must be a point where you can't get energy from either, sort of a most stable nucleus. And it turns out that that most stable nucleus is at iron 56. So a massive star, it lives its life. It prevents itself from collapsing against gravity by using energy from its fusing hydrogen first into helium and then into heavier elements. And then by the end of its life, it has a serious problem. It is fused up to iron in its core, and now it can't get energy anymore. And now it doesn't have anything to support itself against the collapse of gravity, the force of gravity, and it starts to collapse back down. You're up, Cameron. Your stuff is there. All right, so we've made it. We have our iron core. Our iron core has started to collapse. And we run into a problem with, we have very dense neutrons, which is, we're going to treat that as the floor here. So there's a fundamental limit to how many neutrons you can squish into the same place. And when you hit that limit, suddenly pressure reestablishes itself. But we've been falling all this time and you have all this energy from gravity. So something very exciting happens. So we have all of this infalling material. It hits the ground and it comes to a sudden stop. And now there's a shockwave that propagates back out. And that energy sort of is throwing a lot of the material back outwards. And if you have, enough, that's enough to totally unbind the star and push it out. So it turns out, and this is something we've only appreciated in the last 10 years. This is a great picture, right? It's not totally correct. So for a very long time, people have been trying to simulate supernova explosions in their computers, and none of their stars exploded. They were like, what? Why? Why does our star not explode? We have our core bounce, we have this shockwave come out, but all of this other material falls on top of it and causes the shock to, it's called a stall. The shock stalls because of all of this other stuff up above it that is stopping it from going out. So you actually need another source of energy to get the explosion to propagate all the way out to the surface of the star. And that it actually tends to come from neutrinos. So remember that we got our pressure back from neutrons, but initially in our core, we weren't all neutrons. We had protons, we had electrons, and we also had some neutrons. It turns out when you collapse down like that, your protons and your electrons combine to form a neutron, but for mysterious particle physics reasons, when you do that, you also need to make a neutrino in order to conserve the lepton number, which sounds like magic, and it feels like magic to me too, because I'm not a particle physicist. But in order to conserve the lepton number, you need to produce a neutrino. And these neutrinos will stream out, and a very small fraction of them will interact with this shockwave out there, and it'll revive the shock and allow the star to explode. So it's only in the last maybe 15 years now that our supernova in our computers have actually exploded, which is good because we know that our supernova explode in real life, because even the ancient Chinese astronomers also saw that. Okay, so we have the records and we know where this guest star appeared in the sky. If you go and look now at the position of that, you see something really interesting. And that really interesting thing you see is the Crab Nebula. So I have here on the left an image of the Crab Nebula taken with the Hubble Space Telescope, and on the right, an image of the Crab Nebula taken with the EV scope, which we commonly use for outreach events here. And if you measure the expansion of the Crab Nebula, so if you measure like the velocity of this gas, you can actually say, oh, this was all at the same place 1,000 years ago. And it's at the same position in the sky as the guest star of 1054. And if you look at the records of the brightness of the guest star of 1054, that also looks like a supernova. So 1,000 years later, we have figured out the mystery that boggled the minds of the ancient Chinese astronomers. So I think that's a really cool aspect of transient astronomy, this connection to the past. And if you, it's not up right now, but if you come to another outreach event in like 4 months, you'll definitely get a chance to see the Crab Nebula. All right, part 3, the comet ferret. So this starts sort of before the comet ferret. This is a guy named Edmund Halley. He was a really interesting person, actually. I learned a lot about him making this talk. He was the second astronomer royal, so in the England, to the king, because apparently the king needs an astronomer. I actually don't know if that's still a position. That's interesting. Anyway, it is. Oh, cool. You can be astronomer royal today. But he was the second. He dropped out of school to go off to the Southern Hemisphere and make a map of stars in the Southern Hemisphere. That's one of the things he's very famous for. So the first astronomer royal was a guy named John Flamsteed. He did that for the Northern Hemisphere. This guy was like, ah, man, I need to get on this, but it's already been done. So he went to the Southern Hemisphere and made another one and dropped out of school to do it. In 1718, he discovered the proper motion of fixed stars. So for up to this point, people thought that stars in the sky didn't move, but he actually did very, very careful measurements to show that some of them did move, which is what happens is both the sun and them are orbiting our galaxy. But the thing that he's most famous for is probably Halley's Comet. So raise your hands. Has anyone seen Halley's Comet here? Yeah, okay, cool. I really want to see it. So this is a comet that passes through our solar system every 61 years. He was observing this comet in 1682, and he realized by looking at old records that people had kept that it actually looked really similar to a bunch of other comets that had appeared every 61 years. And he predicted that in 1758, it should come back. He did not live to see his prediction filled out, but it was, and in his honor, we still call it Halley's Comet. So it'll be back in, I wrote it down, I think 2040 or something. Whoops, I did not write it down. Yeah, the other thing he's really important for doing is, in order to predict that the comet would come back, then you needed to know something about the comet's orbit. So he had made observations, he had looked at the orbit, and he was trying to figure out the math of gravitation, basically. And so he went to his buddy, Isaac Newton, who was a fairly famous physicist and mathematician at the time. And he asked him, hey, I have this observations of comets. Can you help me figure out this orbit? And Newton was like, oh, I did this math a long time ago, and I lost all the papers. But I'll do it again and I'll send it to you. And so he did, and Halley looked at it and he was like, oh my God, you have figured out gravity. This is so important, you need to publish this. Edmund Halley is actually the one who funded the publication of Newton's Principia, which laid out the laws of gravitation and the laws of motion. It's maybe one of the most important books in physics ever. And it would have been relegated to his back drawer if Halley hadn't been like, hey, this is kind of important. Oh, sorry. So I'll talk a little bit about what comets are. So comets are bodies of rock and ice that orbit our sun in orbits figured out both by Halley and Newton. The ones that are fairly short period, like Halley's Comet, come from the Kuiper Belt, which is about 30 to 50 times the distance between the Earth and the sun. And ones with much longer periods that you maybe see once every 1,000 years come from the Oort cloud, which is 2,000 to 200,000 the distance from our sun. As the icy rocky bodies get close to the sun, the ice and stuff melts off of them. and the dust gets stuff gets thrown off their surface by the solar wind. So you end up with these, the coma, which is sort of the off-gassing material from the comet itself, as well as a trail that, behind you with the ion tail is sort of the lighter stuff that's falling off the comet, and the dust tail is sort of the heavier stuff. So the lighter stuff is almost perpendicular to the direction of the solar wind and sunlight, whereas the dust tail sort of lags in the direction of the comet's orbit. All right, the comet ferret. So when Halley's Comet was coming back in 1758, there was a guy named Charles Messier in France who really loved comets. He loved comets so much that the King of France called him the ferret of comets, which is crazy to me. Like, I can't imagine if the King of France called me the ferret of comets. I don't think I'd come back from that. But Messier did. And so he spent all of 1758 looking for Halley's Comet, but he didn't find it initially. He found something else instead. So he found the Crab Nebula. So before you get too judgy and be like, that doesn't look anything like a comet, right? Messier was observing with about a 4-inch telescope, which is comparable in size to the observing scope that we have used to take this picture, and also was way worse in quality. So it had a lot of like optical artifacts, which have caused this to stretch out and look more comety than not. But any of these like sort of fuzzy things, this would have really looked like a comet in Messier's 4-inch scope. So honestly, even in our new scope, it's sort of, you can see how you could get confused. So he realized this and he was like, hey, I really love comets and I really hate fuzzy things. I'm gonna make a list of all the fuzzy things that I see in the sky so I know that they're not interesting, that they're not comets. So with his friend, Pierre Macan, they decided that they were going to catalog and publish a list of all of the fuzzy nebulosity thingies that could look like comets, but aren't actually comets. And so this ended up being actually kind of what Messier is known for. This is now known as Messier's catalog of objects. The initial catalog was published in 1774 with 45 objects. The final version that Messier published was 1781 with 103 objects. Astronomers in the 1920s gave him credit for another 7 objects. So now the like official Messier catalog is 110 objects total. It includes a whole bunch of different not comets. It includes 39 galaxies, 4 planetary nebula, including one which you will get to see tonight, which is the Ring Nebula up here. This is M57. It includes and 29 globular star clusters, including M13, which is Hercules, which is way up there, and I will not reach it. So yeah, it's very funny to me that something that you wanted to do transient astronomy, one of the things you really wanted to know is not just looking at the transient, but looking at what's already there is so important. Like I think this is a good example and a good way to appreciate the importance of that. I will say he lived up to his nickname, Ferret of Comets. He discovered 13 during his life, which is not too bad. ZTF does better. All right, so we've moved on. We've gone through very early times into the 18th and 19th century. Now we're going to move into the 20th century with the Great Debate. So one of Messier's objects, this is just one example, is M31. So this is the Andromeda, what we now know as a galaxy, but at the time it was known as the Andromedal Spiral Nebula. So there are a few different examples of spiral nebula here. There's M31, M666, M102 also sort of, but you can see M33 is the Triangulum galaxy, but these were all called nebula then, because we didn't actually know that they were galaxies. So at the 1920 meeting of the American National Academy of Sciences in Washington, DC, George Ellery Hale, who was a Caltech faculty and also responsible for building 3 of the largest telescopes in the world up to that point. Actually, this is even before his 3rd, organized a debate on the subject. The title of it was, "How Big is the Universe?" So at the time, the thing people were really arguing about is sort of two aspects of this question. The first is, how big is our Milky Way galaxy? Because at the time, people believed that the Milky Way galaxy encompassed the entire universe. If you wanted to know how big the universe was, then the real question you wanted to answer is just how big is our Milky Way galaxy? But there was a second question, which is, are the spiral nebula their own island universes? Are these things outside of our galaxy? Are they as big as our galaxy? And even at the time, there were some suggestions that maybe that was the case. And if that was true, well, then the universe is not the size of the Milky Way. It's the size of the area and caps which holds all of these spiral nebula. So this would have been very, very revolutionary. This would have increased the scale of what we knew as our universe by a great deal. The debate was between Harlow Shapley, pictured here on the left. He was sort of the young guy. This was actually also sort of his job interview. He wanted to become director of Harvard College Observatory, which was a very, very prestigious position at the time. Even now, Harvard has an incredibly big astronomy department, and is also associated with the Center for Astrophysics there, which is sort of evolved from Harvard College Observatory. So this was a very important job, and this was sort of his chance to go on the East Coast and sort of impress the people who would be giving him this job. He was from Mount Wilson Observatory, which is right there. And his opponent was Heber Curtis of the Lick Observatory, which is just south of San Francisco. It's in the mountains above San Jose. And he was sort of the establishment. So it was Shapley's position that the Milky Way was very, very, very large, about 300,000 light years across, and that the spiral nebula were inside the Milky Way. Curtis thought that the Milky Way was quite a bit smaller, that it was only 30,000 light years across, and that the spiral nebula were in fact island universes. So who's right? Neither of them. They're both wrong. I will say Curtis is quite a bit closer in many ways. So he's only about a factor of 3 off on the size of the Milky Way. And given the observations he had at the time were not unreasonable. But Shapley was very wrong. Of course, we know today that the spiral nebula are in fact island universes, and some of them are even much bigger than our own Milky Way. The Andromeda, for example, is about 10 times the size of our own Milky Way galaxy. It doesn't matter that he was wrong. He still got the job. He became director of Harvard College Observatory in 1921 and held that position for about 40 years and did a lot of really great work in getting their observatories, especially in the Southern Hemisphere, up and running. All right. By 1920, something very important had changed in astronomy. So up till about 1880, and at the time Messier was doing his observations, and the time Halley was doing his observations, if you wanted to tell people what you saw, even through your telescope, you had to write it down or you had to draw it. In 1880, people put photographic plates on the back of telescopes for the whole first time, and like everything changed. I think it's very hard to overstate how much the invention of photographic plates revolutionized the field of astronomy. In some ways, this is actually the birth of our field. If you could tell other people what you saw instead of me, like, just trust me, bro. If you could take longer exposures and be able to see more detail than you could see even if you just looked through your eye of the telescope. And the most important thing for transient astronomy is you could compare the same part of the sky from night to night very, very easily. So I have here 2 photographic plates from the 1890s, which is crazy to me. Harvard Observatories has done a fantastic job of digitizing their entire plate collection. So if you want to just check out this website, it's really cool. You can look and see they have photographic plates going from like 1880 to, I think some of the last ones are taken in the 40s and 50s. So it's a really spectacular resource that they've digitized. I kind of wish that we also had digitized our plates, because you'll see in a minute. So I have here the Orion Nebula is on the left, that was taken at 3:18 in 1893. So you guys are seeing the same thing that some poor cold astronomer in 1893 took a picture of. And then on the right, I have the Andromeda Nebula on October 28th, 1897. So you notice a line across this plate? I thought this was kind of funny. So it turns out if you expect that the glass plates are easy to break, that is true. And if you do it, you apparently have to confess. So we are here to name and shame WJL, who broke this plate on November 7th, 1927. All right, another very important invention is to be able to compare photographic plates you had from the same night was the invention of the blink comparator. It's almost exactly what it sounds like. It's a way to blink between two different photographic plates and compare them. I took the picture on the right up at Carnegie Observatories, which manage the Mount Wilson Observatory. So they're just up on Lake Avenue and Santa Cruz, Santa Anita, something. It's on some street. I've been there. Santa Barbara. So Lake and Santa Barbara in Pasadena. So you see the place where you put the plates is there's one on the left and one on the right. And then you look through that little eyepiece there and there's like a little click switch that you can flick quickly between them. And if you can flick quickly between two plates, it turns out human brains are actually really good at spot the difference. So I have here a set of plates taken from Lowell observatories, looking for planet X, or what was now planet, not the planet Pluto. So there is a picture of Pluto in here. It'll be something that is moving across. Does anybody see it? You can shout. The middle, okay, yeah. So in the middle, you can see over 6 days in January of 1920, sorry, I forget what year. But you can see the planet Pluto moving across the plate. And you can continue to track it and measure its orbit. And this was a discovery made. This was about 7,000 man hours to discover Pluto, of just looking at different plates and blinking between them. There's also actually another transient up there. So if you look towards the top of the image, there's another set of moving objects, which I think is an asteroid, but I couldn't actually find anything relating to it. So I'm not 100% sure. Okay. So we have photographic plates now. We have the ability to compare them to each other. The stage is set for a really incredible discovery. And this really incredible discovery, it was made by Henrietta Swan Leavitt. So during the 1890s, when she was active, women weren't actually allowed to observe on telescopes. This changed really late. It's going to be upsetting. I'll get to it. But they were hired as computers to look at photographic plates. So Edward Charles Pickering, who was in charge of the plate collection for Harvard observatories, hired a bunch of women to look at these photographic plates and catalog them. She looked at the large and small Magellanic Clouds, which we now know are satellite galaxies of our own Milky Way, which are visible from the southern hemisphere. This is one of her plates taken in 1896. These notes on it are actually her own handwriting. And she discovered something really cool about them, which is that there were a bunch of stars that were varying in them. So it was sort of thought that all of the stars in the Magellanic Clouds had to be about the same distance from the Earth. So if you could map their luminosity relative to each other, you know that they're sort of all at the same distance. And she discovered that there is a relationship between the period of the varying stars to their brightness. And this is revolutionary. These stars called Cepheid variables actually allow us to make measurements of distance. If you know how bright something is, if you can measure how bright something is supposed to be, and then you can figure out actually how far away it is. Imagine you're standing on a football field, you have a candle in front of you and a candle at the Harlan Yard line. As long as you know sort of how bright a candle is, you can figure about how far away the other candle is. So this is what Cepheid variables allow us to do. I have on the image to the right here is actually the star Polaris, which is famous for other reasons. It's the North Star, but it's also another one of these Cepheid variable stars. These allowed us to settle the great debate. So Edwin Hubble, who was affiliated with Carnegie Observatories, did a lot of observing with the 100-inch telescope on Mount Wilson. This is maybe one of the most famous photographic plates in astronomy. It's H335H, which is the Hooker plate 335 by Hubble, taken in 1923, where he discovered a Cepheid variable in the Andromeda Nebula. So it's actually, I love this picture. People like to put it everywhere. The Cepheid is actually like way off on the top. Like you really can't even see it. Like you see Andromeda down here. The like actually interesting thing is like way up at the top. But once you've made that, once he discovered this, he realized, okay, I know how bright it should be. It's really faint. This means that Andromeda must be really far away. So it can't be inside our own Milky Way. And that means you know, as big as it is, it must be its own island universe. And suddenly the universe got a lot bigger. He really liked to smoke his pipes. In the photographic plate records that we have from Mount Wilson observatories and also later Palomar observatories, which Carnegie and Caltech went on to build together, there are actually a bunch of like flecks of ash on like a whole bunch of photographic plates. And like now there is a bowl of his pipes that still sits in the Carnegie Library. All right, so we've made it into sort of the modern times. I talked about Mount Wilson Observatory. I'm going to talk a little bit about Palomar Observatory. So Palomar is just about 3 hours south of here. It's a little inland from San Diego. So the same people who built Mount Wilson and built the 100-inch telescope also realized they wanted a bigger telescope. At this time in the 1920s, 1930s, LA was getting stupid bright. So they were like, we don't want to be here anymore. We're going to go to the middle of the desert. And they landed on Palomar Mountain. I encourage you actually to, if you ever have the chance to drive up and visit, the P200 is open, I think from 9 a.m. to 3 p.m. every day. You can go in and like take a look at the telescopes and stuff. But there were 3 telescopes built on the mountain. Initially was the 18-inch, sort of a small one to test and see how the site was. The 48-inch was finished in 1948 after they realized how successful the 18-inch was. And the 200-inch was built and finished in 1949. The 60-inch telescope, which is also important, was built later. It was added in 1970. But this is the current working observatory for Caltech. I spend many, many nights observing with these telescopes. So until 1993, when Keck 1 began operations, the Palomar 200-inch was actually the largest optical telescope in the world. I'm going to talk, which means if you wanted to do astronomy and you wanted to get really good data, you went to Palomar, you came to Southern California, and a lot of really, really great discoveries were made. I'm going to pick 2 different astronomers to talk about completely at random, which is Fritz Zwicky, who was Caltech faculty from 1925 to 1968. He was really interested in supernova explosions. So things like the supernova 1054, he found in other galaxies. He found about 120 during his life, which is really, really impressive in 52 years. He discovered more than anyone. I think until about 2010, his record was not broken. One of his favorite insults, he liked to refer to people he did not like as spherical bastards because they were bastards no matter how you looked at them. So he spent a lot of time alone in his telescope and a lot of time alone with his blink comparator. I also want to talk about Vera Rubin, who was affiliated with Carnegie observatories from 1965 to 2014. She was not a transient astronomer. She measured the rotation curves of galaxies in order to discover dark matter. We can talk a little bit more about that in the question and answer if people are interested. She's interesting. She was also the first woman to observe on Palomar under her own name, which did not happen until 1965. So not that long ago. All right, I have a SAM for scale, just to give you a sense. I'm actually not a huge fan of the P60, so I don't have a picture with it, but I kind of need one now. It gives you a sense. So this is a 48-inch telescope with ZTF on it, and the 200-inch telescope. 200 inches doesn't seem a lot bigger than 48 inches, but it's huge. It's very hard to appreciate the scale of these instruments. So like Harvard, the Palomar and Mount Wilson observatories observed on photographic plates for a long time. We did not digitize our records, and now they actually are all living in the basement of the Palomar 60-inch. So this is the first all-sky survey. So the first like chance you are to have a very good reference to see, then maybe you can look for things to compare to. It took from 1949 to 1958 to complete using the 48-inch telescope. And now all the photographic plates are down in the basement. So if you wanted to go look back and look for transients from a long time ago, you actually had that ability with this survey. I want to talk about today's survey. So the project that I work on is the Zwicky Transient Facility. It is sort of the successor to the Palomar Sky Survey, which now instead of using photographic plates, thank God, we are using a camera, which means someone doesn't have to sit on the back of the telescope and do things all night. They can just observe from the comfort of home or even have the robot observe for them. It has an insanely large field of view for the camera. So here's a comparison. ZTF has 47 square degrees. If you sort of put your thumb out in front of you, that's about half a degree across. So in a single exposure, which takes about a minute, ZTF is seeing a huge portion of the sky. So I figured tonight I would invite you to be a transient astronomer for one night. We're going to look at an image from ZTF. This is from about 8 days ago. And in it, there is a supernova. So on the right is the reference image of ZTF that it took in 2018 when it began operations. And on the right is the one it took 8 days ago that has a supernova in it. So I want to emphasize this is 1/4 of 1/16 of the camera. So there are 16 of these CCDs. When we're looking here, we're just looking at 1/4 of 1 CCD. So this is, crazy big field of view. Does anyone see the thing that is here and not there? It's impossible. You can't, right? Like this is not something you can do by eye. This is something that we have to do with computers. So we do this by computers. The great thing about electronic CCD readouts and camera photos versus photographic plates is we can actually directly subtract one from the other. So if you do that, you have your new image, you have your reference image, and you subtract them off, you see a beautiful supernova. And so this is supernova 2025 TZP. But we're not done yet, actually. So we've discovered our supernova. That's great. Cool. We can watch it for a while. But what kind of supernova is it? What kind of physics happened to produce this supernova? And to answer that question, we need the other telescopes on the mountain. So we discovered our supernova over here on the 48-inch telescope. Now we need to do some kind of follow-up to figure out more about it. So we talked with the Crab Nebula about core collapse supernova. These are the deaths of massive stars when they reach the end of their lives and explode back out. And depending on how much material is outside that core, what kinds of elements you have outside that core, you produce different kinds of supernova. So the Crab Nebula was an example of a type 2 supernova. It had this thick hydrogen envelope around it. You can also have ones that are just covered with helium or just covered with no helium, carbon, oxygen, magnesium, and some other elements. You can also have things that aren't coming from core collapse supernova at all, but are actually coming from the explosions on white dwarfs. So in this case, you might see very strong features of silicon, but not any of these other elements. So we're going to become spectroscopists. This is the time, if you guys want to grab your little thingamajigs, we're going to try and do some on site. We're going to learn how to do spectroscopy. So you want to be looking at the light source. You want to be looking off axis. So we have some pictures here of sort of what you should expect to see when you look at each thing. I'm going to go ahead and mute the video now so that it gets a little bit darker and a little bit easier to see. All right, everybody got their diffraction gratings out? Okay, I'm gonna start with the light bulb so you guys get a sense of how to look at it. So you should see some kind of rainbow. So this is an incandescent light bulb, which was extremely hard to find, actually. So these have all been replaced by LEDs and fluorescent lights, which offer much better efficiency, energy efficiency. But an incandescent light bulb at its very heart is just a material that you heat it up so that it glows. It's the same way if you turn on an electric stove starts to glow. And it's just, it's called black body radiation. It's just thermal emission. So this is an example of a thermal emission source. So you guys see, it's very continuous, right? You see a rainbow without many gaps in it. Everyone good? Everyone had a chance to see? So when we do supernova spectroscopy, we do see what's called a continuum. And that continuum tells you something about the temperature of the supernova. But the main thing we were looking for, remember, we were looking for elements. So how does spectroscopy help us figure out elements? That is what this is for. So inside these tubes are different elements. And I'm just going to run voltage through them to energize them. And we're going to take a look. Okay, you guys ready? Yeah. Okay. All right. So compared to the previous one where we saw this nice rainbow, this nice continuous rainbow, now we're seeing little individual lines. So this is a neon lamp, a neon sign. So the lines you're seeing are the lines of neon. So if you see this in a spectrum of a supernova, that'd be a weird supernova. We don't see neon lines, but it would tell you something about the kinds of elements that are present. All right. Next, I'm going to show you guys one of the most common elements that we see in the universe, which is hydrogen.
Yeah.
All right, so you compare just by eye, the color of the hydrogen lamp is different than the color of the helium lamp. And if you look in the through your diffraction gratings, you see different lines in it. So you can tell the difference between hydrogen gas and neon gas. And this is essentially what we're trying to do when we take spectra on these telescopes. We're trying to look for the elements that are in these explosions. All right. Everyone had a chance to see? Maybe at the end we can have people come up and we'll do it after the thing. Sorry about that. Okay. It's bad to run these for very long because they start to degrade over time and they're very expensive. So yeah, please. All right. And share again. All right, so okay. Okay, cool. So now you guys have seen what I do in a typical day. You can see here are a couple different elements, but they're different lines, as well as black bodies of a couple different temperatures. So what color most of the emission of your black body comes depends on your temperature. Humans are also black bodies in some wavelengths, but we're only about 300 Kelvin. So like, I don't know, like 100 or 100, I don't actually, how 40 degrees Celsius. How hard are we? Like, that's right. 40 degrees Celsius, 98 Fahrenheit. So we emit mostly in the far infrared. So you can see us with an infrared camera, but not with your eyes. This is just a visual spectrum. So you can see if you just measure in nanometers, the kinds of wavelengths of light you're seeing. It ranges from about 740 on the red side down to about 380 on the very blue. So I want you guys to take them. If you want, we'll have a box at the front if you don't want to take your diffraction gratings with you. But if you do, I encourage you to look at a whole bunch of different kinds of light sources, except one. Don't look at the sun. Never, ever look at the sun. If you want to see the solar spectrum, you could get like a piece of white paper and point your diffraction grating at that. But just, yeah, don't look at the sun, folks. All right, back to our supernova. We have, we discovered our supernova on the 48-inch telescope. This one was fairly bright, so we got follow-up spectroscopic observations on the 60-inch telescope. And we got this spectrum. So now we got to figure out, based on what we know of spectroscopy, what kind of supernova this is. So I have to the right a couple of different types of supernova spectrum. Does anyone want to sort of shout out which one this one kind of looks like? 1A, yeah, it's a 1A. Great job, you guys. You can take over for me now. All right. I talked about ZTF. ZTF has been an incredible instrument for transient discovery since 2018. We are sort of at the forefront of transient astronomy, but a next generation transient telescope is coming online, and that's the Vera Rubin Observatory. Oh, I should have said, we named the Zwicky Transient Facility, of course, in honor of Fritz Zwicky, who discovered 120 supernova. And we also named the Vera Rubin Observatory in honor of Vera Rubin. It's located in Chile. It has a much bigger primary mirror, sort of the telescope power compared to ZTF. So it's able to observe things that are quite a bit fainter, but it does have a smaller field of view. ZTF still wins, right? We have 47 square degrees. The Rubin Observatory, which was called the Large Synoptic Survey Telescope until it was renamed in honor of Vera Rubin in 2019. But we sort of got stuck with the LSST acronym. It only has 9.6 square degrees, but it will go quite a bit deeper. So one of the things that a deeper image allows you to do is to find things that are fainter. And one of the things that they're really faint and really hard for ZTF to find, and we'll hear a lot about next month, are asteroids. So we found a supernova. Let's find some asteroids with Rubin. And let this to go. Okay, so we're gonna start. We're gonna look for Rubin. So this is from 3 nights of data. So here we go. 1 asteroid, 2 asteroids, 3 asteroids, 4, 5, 6, 7, 8, 9, 10, 11, 12. In about 10 hours of observations, Rubin found 2,104 asteroids that had never been observed before in 10 hours. That's crazy. So current surveys, like all ground-based surveys, including ZTF and a whole bunch of others, find about 20,000 asteroids a year. So in 10 hours, this got 2,000. If we find 20,000 a year, this thing's gonna blow everyone else out of the water. It'll actually find about 5 million asteroids just in its first 2 years of observations. So I'm not gonna say any more about asteroids. You should come next month. All right. So I really like being a transient astronomer. I think it's really cool to work on things that are evolving on timescales that are sort of meaningful to humans. I like the history of it, that we have this great history both across cultures and also here in Southern California. The one peril of being a transient astronomer is that because things evolve so fast, if something interesting happens, you have to observe right away. So something really interesting happened this week. And the night that I was supposed to have off to practice my talk before this big outreach talk, I actually spent observing. So I have not slept in about 36 hours. Last night, we were observing on 3 different telescopes at once. So both the Keck telescopes here, I don't have my control, so we're doing that telescope we're using to control this laptop. These screens are controlling this telescope. That's the 200-inch Palomar. This is Keck 2, which we are controlling over here. So, if you're a transient astronomer, you're always on call, but it is all right because you have your friends with you. Right. So happy to take questions. Thank you so much for your attention.
Do we have any questions for our speaker?
I noticed a couple slides ago when you were looking at the asteroids, there were a lot of blue ones, but there were also yellow, purple, some different color ones. What do the colors signify?
What a fantastic question that I have no idea what the answer is. So
composition.
Okay.
The composition of the asteroid is usually what it is, but as Sam mentioned, in a month's time, we'll have an asteroid expert who can answer all of those questions related to the asteroids. Additional questions, not about the colors of asteroids.
What was the interesting object?
So, okay, I tried to decide how much I'm actually allowed to say. So I think what I'm safe to say is that if you guys remember in 2017, there was a really exciting astronomical event where 2 neutron stars merged. So you remember our core collapse supernova picture, we end up with this very dense core of neutrons. That actually goes on to form what's called a neutron star, which is just the remnant that's left over with the supernova. These are crazy objects. So a neutron star can have anywhere between like half the mass of our sun to about maybe 3 times the mass of our sun. So maybe 2 times the mass of our sun. They are about 10 kilometers across. So that's from like here to Burbank Airport. So 3 times the mass of our sun from here to Burbank Airport. Like that's you can't think about what that kind of dense. The most interesting physics, I think, in the whole universe happens in these stars. And because a lot of stars are born as binaries, if you guys have seen Star Wars, seen Tatooine, so a lot of stars have companions. If they end up both forming neutron stars, you can actually have the neutron stars merge together. And these form these very, very interesting transient events, both in the very, very high energies and gamma rays, and also in the optical, something called a kilonova. So it's between the brightness of a nova and a supernova. And we've only ever really seen one of these associated with a gravitational wave event in 2017. But about 4 days ago now, we think maybe we have seen another. So that's what we're trying to observe. We're trying to confirm if this is in fact actually a kilonova associated with this potential gravitational wave signal from the merger of these neutron stars.
Lots of telescopes in the world are pointed at this thing right now.
Yeah, we're not the only ones. So we did 3 at once, which is like pretty impressive, I will say. But telescopes all over the world, both in the optical and also radio telescopes, which a member of our panel is more of an expert on radio transient astronomy. So
maybe one more question in the interest of time, and then we'll move to our observing and our Q&A panel.
In the beginning, you said that you change your studies from like something that take like very, very long time to something that's very short term. What defines like something that's take a long time? Like what did you study before that would like cause it to that you would define as long time versus what you study now that's very short term?
Yeah, so I like what I would consider like short term is things that happen like maybe on the outside, like last a year, last 2 years. So something that happens, you know, the time scale, for example, of a PhD is a short term. Whereas you can study things that are much longer term, right? The merger of the Milky Way and Andromeda can take, you know, billions of years. The formation of a solar system is faster than that, but it's even, you know, maybe a couple 100 million years to watch these things happen. So you're never going to be able to see it happen from start to finish. And that's great. I think there's a lot of like really interesting astrophysics there, and a lot of people do really, really great work on that. I find it very appealing that you can watch something from start to finish in sort of a time scale that is meaningful for a human. I enjoy that.
Hopefully no one's PhD is going to be billions of years in duration. We'll get to the question during our Q&A panel. Let's thank our speaker. Wonderful job, Sam. And her tenacity to stay up 36 hours to observe and then give this talk is impressive. So what we're going to do now is, if you want to look at the stars through the telescopes, which I imagine many of you might, we have telescopes set up in the field directly behind here. If you go out the front door and follow the signs around me, you can go there. And in about 5 minutes, we're going to set up the table here. We'll have a brief intermission. We'll set up the table and we'll start fielding questions for our Q&A panel. So if you still have questions that you want to ask, either related to Sam's talk or about whatever, we'll be here for the next 45 minutes or so, but you can go back and forth between the two if you desire as well. All right, we'll be back in about 5 minutes, and YouTube audience will answer your questions as well. So write them into the chat. All right. No problem, guys. Thanks everyone for sticking around. We're going to start with our Q&A panel for those of you who may have some questions. So initially what we'll just do is each of us will go through and introduce ourselves and give a very brief introduction of what sort of science expertise we have, but we can rest assured try and address whatever questions you may have. I'm Cameron Hummels. I'm a research scientist here. My research is primarily in galaxies, how galaxies form, how they evolve, and I study that through the use of computer simulations, trying to model their behavior and their formation and their evolution over the very long timescales that Sam referred to when she talked about things that were long timescales, millions and billions of years, that we're able to artificially speed up time in the computer simulation so we can follow the evolution over these really long timescales.
Yeah, you just heard for a very long time from me. I will say I'm very interested in transients. One of my particular interests is in the dust formed in these explosions. So dust is super interesting, even though all astronomers hate it because it stops us from looking at things we're also interested in. But it's very important for things like forming our own planet. So the planet Earth is really just a very complicated dust grain.
Hi, my name is Delina. I'm also a graduate student here. I'm also a transient astronomer, so I study a lot of the things that Sam studies. But the difference is that I study things primarily in radio wavelengths. I study things in all wavelengths, but my focus is primarily in radio. And the kinds of objects that I study are supernovae, but also other types of transients that are massive explosions, such as gamma ray bursts, if you've heard of those. Or I study things like tidal disruption events, which is when a black hole eats another star, and all kinds of other really energetic events that happen in the universe.
Hi, excuse me. I'm also Sam. Apologies for the confusion that Caltech has an overdensity of Sams. I study binary stars primarily. So these end up forming a lot of high energy events when they merge together, and the processes that form through binary interactions are really interesting.
Okay, so now we open it up to you guys as well as our online audience, and give us all your questions.
So can you tell us more about the Sequoia Dark Sky event? I went to the website. I can't find any information that you mentioned about. There's a talk, there's the telescope. Where is the telescope? The talk, the time, the program. Yeah, thank you.
No problem. Yeah, so they are a little bit sluggish in terms of their organization, which is why when you go to the website that's linked from our website, it doesn't yet have a lot of the details. It just has the date. I spoke with the organizer, the primary organizer of it today, and he said that it would be posted in the next few days, the full schedule. So rest assured there will be more information, but largely Sequoia is a reasonably large national park, and there are a few different kind of visitor center bases within it where they'll be hosting different events. Most of the events will be around the Lodgepole Visitor Center and the Waxahachie Lodge, which is a couple of miles from there. On Friday afternoon, Friday evening, Saturday all day, Saturday evening, and a little bit on Sunday morning. And there will be some activities up at Grants Grove as well, which is about a 45-minute drive, but most of the stuff will be around Lodgepole. Presentations, and then there will be a star party. I don't know exactly what time it begins, but probably at about 8:30 or 9 o'clock at night once it's dark enough to look at stuff. So I encourage you next week, probably, give it till Wednesday or Thursday, and the full program should be available. Yeah.
Hi, so I'm curious about the diffraction gratings, how they split up the spectra. I think it's just a grid of tiny lines, right? And why do those tiny lines cause the resolution of the spectra? Thank you.
Good question.
Really understand this, we need to have a picture. Oh yes, my big marker. Okay, so I'm going to draw a diffraction grating. Oh wait, okay, so I have my diffraction grating and I'm going to put slits in it. So that's essentially like exactly what you said we're doing. So we have a whole bunch of these. We have light that's incoming. And if we think, okay, light is a wave, it looks, so I'm drawing the wave fronts of the light. And then I end up at the diffraction grating. And now each individual one, oh yeah, thank you, Cameron. Yeah, so now coming out of each one, we get another wave now that's propagating in all directions. But now the problem is the wave from this slit could now interfere with the wave from this slit. So if light is some kind of, you know, that, if at, you know, somewhere over here, the wave from this slit is like over here, but the wave from another slit is like down here, they're going to cancel each other out. And it turns out that you have very specific places where you will have the same peak, right? You'll be at peak, so you'll add together, and you'll see, you know, very bright there. And also places where you'll be opposite and it'll cancel out. And because different colors of white have different wavelengths, they interfere and what's the opposite of interfere?
Constructive interference or destructive?
Yeah, constructive interference. Well, they're always interfering, but either like they will destroy each other or they'll construct together something bigger. And so different places along the line will have different colors be constructive and destructive at different places because the light itself has different wavelengths.
So you can think of this, if you're say you're in a, instead of dealing with this in kind of an abstract way in the wave nature of light, think that you're sitting in the bathtub, because baths are nice, right? And you start splashing the water in front of you, and that's causing surface waves to travel away from the point of the disturbance. Let's just say you have a wooden dowel or something, so you can make wave fronts that are just a single parallel front that's traveling forward, much like Sam drew here. These are wave fronts of light, but it works for any kind of wave, a surface wave on water as well. And then let's say you have the equivalent of this diffraction grating that we have that has a grid of lines on it, is effectively in our bathtub is a series of wooden dowels that are sticking out of the water and partially blocking that wave from going forward, but has little gaps in between the various, like spacing between the dowels, so some of the water gets through. That leads to these curved fronts coming out from those gaps where the wave can travel through. So I find that's a little bit more of an intuitive understanding of what's going on. And then, as Sam was saying, as they interfere with each other, you know, the waves coming from this gap and the waves coming from this gap, that's when you get this kind of interference pattern on the side as they interfere and kind of either construct and they both go together and provide a much larger surface wave, or they destruct and they negate each other, and then you don't get that sort of effect. Sorry, I didn't mean to like.
No, that's good. This is a perfect example. I just want to say one thing that's super interesting that we didn't try to do with these is if you think of like sine functions, you can have a sine function that sort of will, I don't know. You can have, if something is like twice the frequency of something else, it'll end up being peaking in the same place, right? Every other peak of the first one will be somewhere else. So you have these like multiples. So with the diffraction gradients, you can see the same effect in the interference with orders. So to either side of the source, you see the first order diffraction pattern. And actually, I did try it with these. If you choose like a fairly bright light source and you move even further off axis, you can even see the second order diffraction. And you'll see that it looks slightly different. You end up with it's called a sync function. So you sort of start out like this, and then you sort of, maybe I'll just draw that. Yeah, let's do, make a better pen. We're like totally pen. Yeah, big fat pen. Okay, so a sync function is like a sine function, but it's syncing. Thank you, Sam, for laughing. All right, so we have our sine function, and then we're also, I'm so bad at this. Is the worst sync function ever. Can you do better, Sam?
Let's see.
Yeah, you have your like main thing, and then it.
Yeah, so it gets smaller wiggles. Yeah, that's a good sync function. It's not symmetric, but you know. So this is like our first order ones. So this is our main peak, right? The one that's not interfering. And then we have like our first order diffraction, and our second order, third order, fourth order, fifth order, and you have that for all the colors. So I encourage you to like take your diffraction grating and try to look even further and further off axis, so you can see the evidence of the waves interfering with each other.
Additional question.
So another question about the diffraction grating. So if you point it at sunlight, not looking at it directly, you will see the patterns for, say, calcium, because sun has calcium. You'll also see for hydrogen. How do you know the relative abundance of those two elements?
Ooh, that's a very good question. And it's hard, right? So the lines that we see depend on a lot of different things. They depend on the temperature. They depend on the density. And they also depend on like the relative abundances. So the fact that you see the calcium lines in the sun, I'm not super familiar with this line, but it is a very common one that you see. And it happens to be that the temperature of the sun, the surface of the sun, the gas and the densities and stuff are right to form that line. It turns out actually the sun doesn't have very strong hydrogen features. It's sort of a little too cold for that. So even though the sun is mostly made of hydrogen, you don't see very, very strong hydrogen lines like you see much stronger calcium lines. So in order to figure out like what your spectrum is telling you about the composition of your object, it's not enough to just see a line. You also have to know something about the temperatures and densities involved, and then do some complicated quantum mechanics and figure it out.
But you can model all of those simultaneously. So if you might see a couple of calcium lines or a couple of oxygen lines or a couple of hydrogen lines, all of those tend to occur at different, as Sam was saying, densities and temperatures and different ionization states of the gas. And if you model that all together, you can get kind of a broad picture of A, what the composition is, B, what the density of those relative metals or ions are, as well as the temperature structure that's there. But it absolutely is a challenging.
Yeah, it's really hard. It's actually one of these things is super interesting. You would think like, oh, we should know, we've been doing spectroscopy for hundreds of years now. We should really know what the lines of all the elements and stuff are. But this is actually something we're still figuring out. Someone recently had to rewrite a paper that they had used doing JWST data because the spectral line models that they had were wrong for some like very, very common element. It was like sodium or something. I don't remember exactly. And a lot of these stuff is done in lab experiments, but it's hard to recreate the conditions that we see in space, these very low densities of these very high temperatures and very interesting situations. So it's actually very sad. The NIST does a lot of these lab experiments and a lot of this like database keeping and stuff, and they were recently shuttered by budget cuts.
The National Institute for Standards and Technology. It's in Colorado, and it's the people who keep like all the atomic clocks that keep things synchronized between different places, or things like these emission and absorption lines from lab resources and such. So yeah, it's a lot of important stuff. Unfortunately, it's getting shut down. Feel free to chime in if you guys have stuff to add as well.
I can say the other fun thing about spectral lines, this isn't about the sun, but we can use spectral lines to tell us more about a lot of different objects in the universe. And sometimes the challenge is not only if you're looking at the sun, which is really, really close to us, you should know for each of these elements roughly from our lab experiments what wavelengths of light we should be seeing. So you should know if you look at a spectrum, you should kind of know where you expect those lines to be and how bright they should be or how tall they should be or what they should, how wide they should be. But once you're looking at objects in space, kind of all bets are off. because there are a lot of different processes that affect how wide those lines are and affect how tall those lines are or bright those lines are. And the other thing is that the further away an object is, something comes into play called redshift, which is basically just the further away an object is, the redder it will look, literally the color red in terms of the wavelength of optical light, which means that the wavelengths that you think those lines should be at, if it was right next to you, right here on Earth, are no longer true. So it's really fun when you're doing transient astronomy to get a spectrum of an object and you see lines. And even if, this is a line in the place where you think that a hydrogen line should be, it might not be a hydrogen line. So it's a fun little puzzle that we have to deal with.
Right. Question. And then I'll ask one from our online audience. They've been patient.
My question doesn't, I don't think, because I don't know about astronomy, I don't think it has anything to do with tonight's presentation, but I'd like to ask it anyway. Thank you. About 5 or 6 weeks ago on KPCC radio, I heard an announcement about something astronomical. And I was very surprised because I've never heard a radio station announce something that happened up in the universe. And it was that there were 2 black holes that were merging. You know about this? Yeah?
A lot.
Oh, it happens a lot. Then my question is nothing. I was going to leave. I was going to ask, was there anything new that was learned from this or that was reinforced from this?
This is actually a great question. So everything that we've talked about tonight, does this even work? Oh, okay. Never mind. It just sounds like normal to me. So everything that Sam talked about tonight involves light. So all the signals that she gets about supernovae in these that she showed are light that we got from explosions that traveled all this way. But light is not the only thing that carries information in the universe. And Caltech has another very famous big observatory that we call LIGO. It's the Laser Interferometer Gravitational Wave Observatory. And what LIGO detects is vibrations in space, literally in space, from big objects merging. And LIGO has been going since, I think the first discovery was 2016. Someone correct me if I'm wrong. Right, yeah, the first astronomical discovery was 2016, I believe. And since then, LIGO has detected a lot of black hole mergers. Because these objects are really large, they wiggle space-time a lot. And sometimes, every once in a while, LIGO will detect something smaller, not small, like neutron star mergers. But yeah, so we find out about these not from the light they give off, because they don't really give off much light, because black holes have no light. They have some gas around them that gives off light, but primarily their energy is transmitted in gravitational waves. So not a dumb question at all.
LIGO is the reason I've been awake for 36 hours. So the observations that we are looking for now with all our telescopes is we're looking for these smaller merging things, which actually do have light in them. So that's why we're trying to point our telescopes, which look at light, to these things. So about 5 days ago is when the news that you heard, instead of 2 merging black holes, it was 2 merging neutron stars. So
the other thing that merging black holes can tell us about is, so you said this a little bit, so they release things called gravitational waves. And when we talk about wiggles or vibrations in the universe, you may have heard something about space-time or a fabric of space-time. What gravitational waves are actually doing, which is a very metaphysical, abstract way to think of it, is physically moving the universe. So whatever makes up the universe, however you want to think of it, it's physically moving that. And one of the reasons that we want to study these black hole mergers, even though they happen quite often, is we're trying to understand a lot about how the universe formed and how it works. And black holes themselves, we actually do not understand particularly well, which you probably know and you've probably heard. So the more of these events that we can look at and the more that we can detect, the more we can learn about black holes themselves and also where they came from and how this might have affected the evolution of our universe. So even if one individual event is not particularly special or interesting, it's very important for us to be able to learn about all of them so that we can understand more about everything that would have contributed to them.
And I believe the event that you may be referencing, because there was a press release associated with one of the recent LIGO gravitational wave emissions that were detected of a merging binary black hole, was that the black holes were very massive, and they produced the most massive black hole that had yet been discovered using gravitational waves. And this took place there was a press release about this a few weeks ago, so it was in the news and so on and so forth. And so I believe it was like a 140 solar mass black hole, so about 140 times the mass of our sun, that was merging with another one that was about 100 times the mass of our sun. And the product, you might think you just add 100 plus 140, it should be 240, but the product was actually about a 220 solar mass black hole. And the reason it's less than the sum of those two things is because that additional mass was converted into the energy that generated this rippling of space-time, the gravitational waves that we were able to detect. So that's why, 1 and 1 doesn't always equal 2 in the context of this. 1 and 1 is like 1.8 when you add them together. And then that 0.2 goes out and is converted to energy to actually move the space around it and the space-time around it. Okay, I promised an online audience member that I would ask a question. So there was a question about T Corona Borealis. So there is a star, also known as the Blaze star, that the question was, are there any updates on the status of T Cor Bor? And why are there different predictions for its next expected outburst? So does somebody want to explain what this object is? Or I can if nobody wants to.
Oh, okay. I can maybe say a little bit.
Sure, please.
Okay, so
I should also mention we had a stargazing lecture on this about a year ago at this time, given by Professor Monsi Kosliwal, who's a professor in the department and working with Sam.
yeah, she's my advisor. She's in that picture actually that I showed at the end.
Yeah. But go ahead, please.
Yeah. So T Cor Bor is a recurring nova. So I didn't talk about nova in my transient astronomy talk, which is a little bit bad of me to do. These are some of the most common transients that we saw for a very, very long time. They're almost exactly what they sound like. So nova is new. It was new stars that appeared in the sky. And these are the burning of hydrogen on top of a white dwarf. So these are also coming from binary stars, like Sam studies. It's a white dwarf with some kind of companion, and that companion is giving material to the white dwarf, and you continue to get material to the white dwarf. And if you get enough material on the surface of the white dwarf, the surface of your white dwarf actually turns into a hydrogen bomb, essentially. And that causes the star to get crazy, crazy bright for a couple of days before fading back away. So T Cor Bor is a T Corona Borealis. If you're in the know, cool kids call it T Cor Bor. Is an example of a nova. It's a type of nova called a recurring nova, which means it's building up material quite fast, and it tends to repeat quickly. We think most nova actually are repeaters, but they're repeating every like 10,000 years. So that's less good for us. So it was expected that in like September of this year that T Cor Bor should have accreted enough material to go nova again. But we didn't see that. And then it moved behind the sun. So when it's behind the sun, you can't actually see the light from it. And we're still waiting for it to come back. So it could have gone while it's gone, while it's behind the sun, and we missed it, and that's sad. Or when it comes back, we'll see it. I actually am not a super expert on exactly the predictions for when we expect it to get bright enough. I think it has to do with some observations. I don't know if Cameron, you know anymore or remember Muncie's lecture.
So it was observed to have gotten brighter like 80 years ago or something like that. And I think prior to that, it has essentially an 80-year period between the brightnesses, but that was only categorized by, I think, two previous observations, 80 and 160 years ago. And so people made the prediction that this was meant to go off sometime last fall, like September, October, November. And so we had a lecture about it in like August, and it was like, look out, this is going to be great. You're going to be able to see it. And then nothing happened. And everyone's like, what the heck, guys? I thought this was supposed to happen. And nothing has happened since then. So I guess that's what you get when you try and come up with like a hard and fast rule based on two observations. Like if you see what's a good analogy? You see something happen twice and you assume the third thing's going to happen on the same time scale. It should probabilistically do that, but there can be fluctuations depending on the nature of the explosion on the surface and the feeding process.
Yeah, exactly. So the physical mechanism which triggers the explosion is you just need to get dense enough at the bottom of the layer of hydrogen in order to ignite fusion. And it is very probabilistic. It's not happening on the entire bottom surface layer at once. There's like a little tiny place where the density just barely gets high enough that you ignite fusion. And as soon as that happens, like the whole thing goes off. Like it's like if you strike a match, right? The whole match ignites, even though the deflagration started just on one side of the match. And so sort of the point that you get enough like hydrogen in this layer in order to be able to do that is somewhat uncertain. But yeah, so it's possible that we'll see it happen when it comes back from around the sun, or it's possible that it will have gone nova while it was actually behind the sun, in which case we sort of are SOL.
Okay, additional questions? Yeah.
Thank you. So since today not too many people, I think it's a good opportunity to ask more questions. I mean, I remember last time it was filled with people, and yeah. But anyway, my question is, I read like some article on the life cycle of star, and usually the starting point in the article is is a bunch of studs, hydrogen atom, and then gravitational pull them together. So but if you look at the end point of those articles, is that depend on the mass, some will become black hole, some will become neutron stars, some will become dwarf, like dark dwarf or whatever. But it's not going to be a bunch of dust or hydrogen. So I don't see a cycle there. That's the first question. Second question is, okay, even if the beginning of the star is a bunch of dust and hydrogen, where does that come from? I mean, or what happened before that? Okay, some people said maybe Big Bang, things like that. I mean, then I will keep asking, like, what caused the Big Bang and what happened before the Big Bang, right? So that question keep going on. So this type of question, like, kind of bothering me all the time when I read those articles. Thank you.
Okay, so just to summarize, the question is, what is it that leads to the formation of stars, and how, why are some stars different than other stars? Is that kind of the first question?
That's not my question. I know it's dependent on mass. My question is, if it's, okay, the starting point is a bunch of dust and
gas.
hydrogen.
Yeah, that's right.
But if you look at it, they talk about the life cycle, the end point is not dust and hydrogen. So that means at the end of the universe will be a bunch of black hole star. I mean, I don't see a cycle.
There's not. There's no cycle. We don't, I mean, there are some people who will claim that our universe is a cycle and that, okay, this is a big question. So
Yeah, so I'll start it out. Okay, so the sun is about 10 billion years old. And the universe is about 13 billion years old. So the sun has been around for the majority of the universe's lifetime. Is it 5 billion? I'm sorry. It has not been around for that long.
Yeah.
There are, my bad. Thank you. Yeah. There are stars in the galaxy that have been around for a lot longer, for about 10 billion years. So a lot of smaller stars than the sun can survive for a very long time because they mix everything in their atmosphere. So the sun has a like definitive core where it fuses hydrogen, and it has an envelope where it doesn't do that. And eventually it'll run out of fuel in the core. But if you, by the time the sun explodes, it will not have run out of all of its hydrogen. So there are other stars that are smaller than the sun. They're what we call fully convective, which means they mix entirely. They don't have like a definitive core and envelope. And those stars have to use all their hydrogen before they move on to their next stage. And so they last a very, very long time. And those actually make up the majority of stars in the universe. They're M dwarfs, small stars. And so a lot of that material does get trapped in stars, yes. But most of the dust that forms stars does come from the beginning of the universe. But a lot of it, some of it has been recycled from early stars that died, and a large amount of their dust was kept in a remnant, and some percentage of it gets blown off. So every time, I guess, you make stars, you are keeping some more mass trapped. And so this cycle cannot go on forever. I don't know, Sam, you know probably how much mass gets blown off every time.
Yeah. So if you have a star that's about like 20 solar masses and you make a neutron star that's like maybe 2 solar masses, then 18 solar masses of that star is free to go back into what we call, astronomers are very clever. So it's the medium between stars. We call it the ISM. It's the interstellar medium. So actually, if you start with the Big Bang, most of the elements that you have are just hydrogen, helium, and a little bit of lithium. In order to get all of the heavy elements, things like carbon that like make up you and I, things like oxygen, these are actually all coming from stars, like entirely from stars. And it's from this process of fusion that I showed earlier that you're able to form those heavier elements, and a lot of those heavier elements go on to form dust grains. So this is actually what I mostly do in my own research is I work on the formation of dust grains of carbon, grains of silicon, grains of oxygen, and aluminum, and all kinds of these heavier elements sticking together. And these are all forming in these supernova explosions. So sort of the people like neutron stars, people like black holes. They don't like so much like the stuff that is blown off in the explosion. But the stuff that's blown off in the explosion does form a whole bunch of this dust, which then goes on to form the next generation of stars. To your question about the life cycle, especially the Big Bang, this is very interesting, right? So the first generation of stars actually weren't formed in these dusty clouds, right? There was no heavy elements to make dust at that point. There was no carbon, there was no silicon and stuff. So these stars may have been very different than the stars that we see forming today. So we call these stars population 1 stars, and population 3 stars. And we've actually never observed a population 3 star, right? Because these are from the very beginning of the universe. If you wanted to see a population 3 star, you need to go look back. You didn't form stars right after the Big Bang, maybe 200 million years after the Big Bang, you can see the first like population 3 stars. But in order to do that, you need to look very, very, very far away. And of course, if you're looking very, very far away, it's hard to see individual stars. But that's a really good question. Like the process of getting from the Big Bang into this cycle of, we call it just obscured star formation, which dominates in the universe today. It could not have been the dominant process early on in the universe because there just wasn't enough dust.
But So the question is just to make sure that the online audience can hear through the microphone, is the Big Bang Theory proven? There is a misconception that basically says that theories are either proven all the way 100%. No theory is proven 100% all of the way. The Big Bang hypothesis or theory has several different pieces of evidence that support this interpretation. We see an expanding universe. We see the abundance of hydrogen and helium that's consistent with that being produced in the very first couple of minutes of the existence when things were much denser and nuclear fusion could take place. We see the light echo from that flash of the Big Bang in the form of the cosmic microwave background. All of these things point towards that interpretation. But for no theory do you have 100% clarity and confirmation that that is true, but it's very, very good. I would say amongst modern astrophysicists, like trained astronomers and astrophysicists, 99.99% of them believe that the Big Bang Theory, also known as the lambda cold dark matter scenario of the universe, is the accurate portrayal that fits the evidence, the accurate theory that fits the evidence that we see. But I think one of your initial questions was, is it cyclical? We see things in the early universe that look, the formation of this gas and perhaps dust that might be around in the early universe. And then what we predict will be in the late universe, way, way, way in the future, will look very, very different from that, with black holes and perhaps neutron stars and kind of a thermal bath of radiation that's everywhere. And that is very different. And I don't think many astronomers, current astronomers, believe that that will somehow cycle back to the start. There's speculations and there's lots of hypotheses for how the universe will change over time. And some of them are these kind of repeating cyclical things, but I don't think that's the main interpretation that most of the astrophysicists in the world believe currently. Does that help address the question you had?
If I can do it,
okay.
What do you think, like, for very, very long time later,
yes,
the universe will look like?
What do we think the universe will look like in the distant future? In the very, very distant future? The common interpretation is that it will continue to expand and that galaxies will get so far apart from each other that they're traveling faster than the speed of light away from each other, not because they're traveling that fast, but because space itself has expanded to that rate and they're just along for the ride. And so they will be outside of our light cone and we won't be able to see any other galaxies. Right now, you look up in the night sky and you can, even the Messier objects that Sam was talking about earlier, many of those are distant galaxies like our own Milky Way. In the distant future, they'll all be redshifted out of our field of our ability to see them, and we'll only see the stars in our own galaxy. And then most of those stars will die off and fade away and either turn into black holes or white dwarfs and eventually fade to black dwarfs and just be kind of bumping around, and we won't see anything really in the night sky. So it's not a very bright future, both in the optimistic bright as well as the luminous bright, but that's kind of the prediction for what our distant future. This isn't like 10 years off. This is like 10 quadrillion years into the future. And of course, we can make lots of predictions about something that we're never going to be able to see. So it's an easy prediction to make. I'm going to call on somebody who hasn't asked a question yet.
Thank you. So today we learned about these transients and I think these days there are artificial transients like satellites, a lot of satellites. I heard that Starlink satellites affect your kind of research. How serious is it, and is there any kind of way to overcome those?
So I'm a radio astronomer, which is why I'm grabbing the microphone here. So it's very serious. Satellites are a problem in a lot of different wavelengths. So in the easiest one for us all to relate to is optical. Typically, when you launch a satellite, you want to literally paint the satellite so that it is reflecting the least amount of light from the sun possible. It's still not going to block all of the light that's reflected from the sun. So when you take these images through through telescopes, you can see it when you're observing. Sometimes when you're observing and looking through the camera, you will literally just see something go across your screen. And that means that for the second that that satellite was in your screen, whatever data would have been behind that satellite is not usable to you. So in optical, painting the satellite is something that you want to make sure that you do. I have heard that Starlink was not very careful about that. So they are a problem in optical wavelengths. In radio wavelengths, satellites primarily communicate through radio wavelengths. That's how we use our cell phones. That's how we use Bluetooth. That's how we use GPS. And all of these things, this is how we use Wi-Fi. And you know that all of these things have gotten really, have made really great strides towards being better and more accessible for all of us. And that's great. But again, there has not actually been a lot of regulations on what you can put up in space, how often you can put these things up in space, how many things you can put in space, and then what wave bands in terms of radio frequencies are actually allowed to use. And so in astronomy, we can see all of this interference. So all of these cell phone signals, all of these Wi-Fi signals, all of these GPS signals, all of these satellite communications we can see. And the earlier agreements that we had with before basically all of these things were so prevalent, because Wi-Fi didn't exist when we first started doing radio astronomy, was that these would be constricted to certain wave bands. And then us as astronomers would just know that these wave bands between these frequencies, we just can't observe. That's what we use for cell phones. So we're just not going to use them. But the bounds of basically the radio communication that we use now has expanded beyond the bounds of what it was decades ago. And so now it's becoming a problem where every single night when we look at the sky, a lot of our data is unusable, and because of all of this interference from satellites. It's so serious that in the radio astronomy group here at Caltech, we have someone, so we're trying to build a new instrument. We also have two instruments that have been already built by Caltech, the long wavelength array and the DSA, which is the deep synoptic array. These are two, we have a bunch of radio instruments at the Owens Valley Observatory up near Bishop. And we have someone who never intended for this to be their job, but basically their sole job right now has been to study the interference coming from Starlink and other similar satellites, but primarily Starlink, understand how their frequencies are affecting our measurements, and communicate with the company to try and see how we can regulate this to prevent basically radio astronomy from being completely impossible in the next few decades, which sounds like I'm being very dramatic, but unfortunately it's a serious problem. We're looking at, if this keeps up and we do not have regulations for putting satellites like this up into space and cooperation between companies and astronomers, we're seriously looking at the death of this field, which is, again, very dire pronouncement, but yeah, it's a serious problem.
About that? Yeah, other than price.
Well, right. So it depends on what you're trying to do. So absolutely, it's way more expensive. It is way more difficult. There are way more things that can go wrong when you're doing that. And it also depends on what you're trying to do. So for some telescopes, like you just heard James Webb went up, it's an advantage to us to put Webb in space. There's a lot of problems that are solved by putting that telescope in space. For radio telescopes, which is my experience, the kind of science that we do with those radio telescopes, there's not a whole lot of advantages to, well, I should say there are a lot of advantages to putting radio telescopes in space, but it's not really as feasible, because when most of the instruments that I work with are not just one telescope, it's these massive arrays of like 20 different dishes that all work together to form an observation. And so in space, you just can't do that because they're literally, affixed to the ground. If you have a bunch of satellites in orbit, you're not going to get the same effect as what we have on Earth. So you would have to basically change the technology and change the way that you do these observations. And there are ways to do that, but currently it is way more advantageous to us in some cases to make sure that we can continue to use the infrastructure we have on the ground.
If you want to build a telescope on the ground, it costs, let's say it costs X dollars to build. Putting it into that equivalent telescope into space, it just increased it by, it's like 100X or 1000X. And it's harder to maintain. If you have a car here and it breaks down, you can take it to the shop. But if it's up in space, I mean, good luck.
Yeah, I'll also say even if you go to space, that won't necessarily help you for satellites, depending on what your orbit is. So this is actually a major problem with the Hubble Space Telescope. So Hubble Space Telescope is in a low Earth orbit because it was designed to be serviced by shuttle missions. But that means that there are satellites in orbit above it. And that field has gotten a lot more crowded. So a lot more, even if you are in space, you're still plagued by satellites. The other thing I will say, just because I hate Starlink so much for what it does to observing. So like Delina said, when you launch your telescopes, you want to your satellites, you can orient them more carefully so that you avoid reflecting light down onto the ground. But when you're still launching into orbit, you miss this. I know every time Starlink launches, just from ZTF data. So I will see every time a new set of Starlink satellites goes up, I see a whole bunch of things that are not supernova and are satellites until they're able to orient back down and the numbers become more manageable. But yeah, it's a huge problem for all wavelengths and all bands, and worse for radio, maybe even than optical.
Questions? Yeah, but you've asked a question. You've asked a question. Any new takers? There's one online actually that I think is a good question, and that is, are there any updates with 3I Atlas? This is a new interstellar comet, a comet that came from outside of our solar system. It's only the third object that we've been capable of seeing that came from outside of our solar system into our solar system, and it's just doing a flyby. The other two were observed over the last 5 or 6 years, Oumuamua and Borisov. And so this one was discovered about a month and a half ago, and over the next few months, it's going to do just a flyby through it's traveling at like 40 miles per second, and it's just doing a flyby. It's in no risk of striking the Earth, but it'll come as close to the sun as about Mars, and then just keep going. So the question was if it had shown any kind of, if they'd classified it as a comet or an asteroid, and I think it is now classified as a comet because it's showing a tail just like comets do, and like we saw the Messier, the ferret of comets, discovers all these comets, and so you have this tail behind it, that tail being caused by essentially as it's made up of ice and dust, and as it gets close to the sun, it heats up and it evaporates and causes the evaporating ices to trail out away from the sun. And so we're starting to see that with this interstellar comet as well. Any other questions before we finish it off here? Or shall we leave it on the note of this icy interloper? Okay, one more question.
I just love hearing these answers from people. This is for all of you. What is your favorite part of your research?
Favorite part of your research? Is it staying up all night before you give a public lecture to observe on the largest telescope in the world?
So Keck is not the largest anymore. We got beat.
It kind of is. Okay, so let's talk about this. The Keck telescopes have, when we talk about the size of a telescope, we're talking about the size of the aperture of the telescope. So the telescopes out there that you may have gone out and looked through, those are like 8-inch aperture. And the larger the aperture, the more light you allow through to focus down onto your eye or onto a photographic plate. So you really want to, goodness gracious, you really want to increase the size of that aperture. The Keck telescopes, which were built in 1990, have 10 meters, 30 feet across. The aperture is very, very large, like the size of this room. And then about 10, 12 years ago, there was another telescope that was constructed that's like 10.1 meters inside, just so they could say, it's not 10.8? No, 10.2. Yeah, exactly. So it's a slightly larger, but I still consider Keck to be the largest. But right now under construction is the ELT, the extremely large telescope. That's its official name. In Chile, and that will be 30 meters across. So nearly 100 feet in diameter. It's really going to dwarf this thing. So anyway, we got off topic. Talk about your favorite thing, and I'm going to go find out what that crash.
Yeah, sure, I'll start. Okay, so working on binary stars is really interesting because there's so many different types of just single star. And then if you put a bunch of stars together, you increase the amount of different types of systems by like an order of magnitude. And so you'd think like, oh, there's billions of stars. The Zwicky Transient Facility observes like 4 billion stars. And so you'd think, oh, okay, out of like 4 billion stars, you've probably already seen everything there is to find. No. We are constantly finding new types of star systems. And I think it's so cool to like just sift through reams of data and find like the 1 to 5 out of 4 billion objects that are doing this like one specific weird thing that you can't explain, and then go through the physics and get a bunch of more data to like figure out what it's doing and prove it. And then it gets written up and people are like, that's really cool. That's my favorite thing.
Let's see. So I actually do like staying up all night. It does get very old when you do it very often, but I actually don't. So I still think it's very novel every time I get to use a really big telescope. So that's really fun. But for me, I really like puzzles. And doing what I do is kind of like doing puzzles every day because since I work in radio primarily, a lot of the ways that I find objects is just we do these massive all sky surveys using radio telescopes, and it gives us a bunch of dots. And so I get a dot and I see that that dot was not there 1 year. And then 3 years later, there was a dot there. And then 3 years later again, which is the next time that we saw that part of the sky, it was gone. And that's about all of the information that I get from that one telescope. So then what I have to do is go to every other available database or telescope or archive or place that I could find any data about what that might have been and try to put all of these different clues together that I get from all of these different sources and different wavelengths and figure out what that dot was. And I actually think that's fun. So.
Yeah. So right now, I really hate staying awake all night, like so much. It's been a long week, you guys. But yeah, I really enjoy looking at stuff. I think one of the things it's easy to forget when you're doing science and trying to understand the natural world is that humans are also a part of that world. I really feel like you know, as a human being, I on Earth and stuff, the things that make up me are not different at all from the elements that make up the universe. I like to say like humans are the universe arranged in such a way that it can learn about itself and explore itself and look at itself. And I think it's a really beautiful sort of, I see it as a cosmic self-discovery. And I think that's a really cool position to be in. And I like to be able to contribute to that understanding, the universe's understanding of itself. And I find that very powerful, although maybe not powerful enough to stay awake tonight.
I like coding. I really like writing software and then looking, you know, to analyze something and then looking at the results in a graphical format and gaining some sort of insight from a system. I think that's really exciting. Okay. Thank you guys. Let's thank our speaker again and our panelists. Thank you guys. Thank you guys for sticking around so late. Again, our next event, one of these will be Friday, October 3rd on a talk all about near Earth objects and asteroids and comets in the inner solar system. So you can bring all of your asteroid questions. Our next Astronomy on Tap will be in 3-ish weeks on Monday, September 15th, all about the possibility of living on Mars, us living on Mars, as well as sending telescopes up in effectively hot air balloons into the upper atmosphere to get above much of the atmosphere and take observations from there. And then, as I mentioned, there's going to be 2 dark sky festivals that we're helping out at, Sequoia and Great Basin National Parks in the middle of September. Thank you guys for joining us. We'll see you guys next month.